I'm James Wahlberg, and I'm going to talk to you about electrolytic cells. We'll begin by learning to identify the parts of electrolytic cells. I think you'll find that these cells have a lot in common with the other kind of electrochemical system, the galvanic cell. So we'll start by finding those similarities, and then we'll talk about the differences and learn how to apply those differences to electrolytic cells. Let's get started. To begin then, let's talk about what galvanic and electrolytic cells have in common. They both have reduction occurring at the cathode. I'll remind you, if you've seen these mnemonics, of the first of three animals, the red cat. That helps you remember that reduction happens at the cathode, and that's always the case for galvanic and electrolytic cells. They both have oxidation occurring at the anode. And here's the second of three animals to help you remember that, anox. So oxidation at the anode. Finally, both types of cells, galvanic and electrolytic, have electrons flowing from the anode to the cathode. And to help make sense out of that, I'll remind you of a third animal, which is Leo the lion, and lions say grr, so Leo says grr, which helps you remember that loss of electrons is oxidation, gain of electrons is reduction. So if you put that all together, if the anode is losing electrons and the cathode is gaining electrons, that means the electrons are flowing from anode to cathode, and that is the case in both types of cells, galvanic and electrolytic. In terms of what electrolytic cells can look like, there's a couple different configurations, and I'll show you two of them here. One arrangement is to have two separate half cells represented by these two separate beakers, and in each of these beakers there's a solid metal electrode. There's also here this U-shaped tube. It's a salt bridge, which is something you've probably seen in a galvanic cell, but that could exist in an electrolytic cell as well. Another arrangement is to have one half cell represented by the single beaker on the right, and here both electrodes, both solid metal electrodes, are in one solution. So it could be arranged either way for an electrolytic cell. The key feature of all electrolytic cells, however, is that they have a power source in them, represented here by a battery. And the reason that electrolytic cells always have a power source is because these are not spontaneous systems. This is analogous to having to push a ball up a hill as opposed to the ball rolling down the hill spontaneously. So in terms of the energy then, the Gibbs free energy, we're talking about a delta G that is positive, is greater than 0. Now an expression that connects electrochemical systems to free energy is delta G equals minus NFE, where N is the number of moles of electrons transferred, F is Faraday's constant, it's a large positive number, and E, with that funny little circle, the E naught, is the reduction potential of the system. Now, reduction potential is just what it sounds like. It's the potential to be reduced spontaneously. Think of some other potential, like your academic potential. If you have a high academic potential, that means you have a larger positive number for your grade point average. Or if someone has a low academic potential, they will tend to have a lower number for their grade point average. So too, for reduction potential, the larger and more positive the number is, the larger is the possibility or the likelihood that a system is going to get reduced, which means it's going to gain electrons. So putting this all together with the Gibbs free energy, that means that we need a value of E naught, the reduction potential, that is less than 0, is negative, because in order to get a positive value for delta G, we're going to need another negative in this expression because we already have one minus sign. We're going to need another negative value to end up with a positive value of delta G. So that's just a little bit of algebra to help you see how the value of the reduction potential connects to the idea that electrolytic cells are non-spontaneous systems. To go on then and identify the anode and the cathode in an electrolytic cell, we can take advantage of this idea of the reduction potential. So the electrode with the lower reduction potential, the smaller value, is the cathode. And the electrode with the higher reduction potential is the anode in an electrolytic cell. Now, keep in mind, as I said just a moment ago, that the reduction potential is the potential for an electrode to be spontaneously reduced. So we would expect reduction to happen at the place where that potential is higher. However, these electrolytic cells are non-spontaneous. So that means we expect the opposite. We expect that the cathode, as is always the case, where the reduction will occur, and the anode, as is always the case for both kinds of cells, is where the oxidation will occur. But in a non-spontaneous system, instead of expecting the reduction, the cathode, to happen at the place of the higher reduction potential, in this non-spontaneous system, it's the reverse. We expect the electrode with the lower potential to be the cathode, and the electrode with the higher potential to be the anode. So this is opposite for electrolytic cells versus galvanic cells. All right, so in terms of the sign on the electrodes, we've shown how to identify the cathode and anode. There's one more convention, and that is where we put the plus and the minus sign. So electrolytic cells have their cathode marked as negative, and they have their anode marked as positive. One easy way to keep track of that is to just pay attention to the power source. Pay attention to the battery in this case. The short line on the battery symbol is where the electrons come out of. Electrons are negative, therefore that's the negative side of the battery. And the other side, the larger line, is the positive, so that's where the electrons go to. So you can see that the battery is connected on its negative side to the cathode, therefore the cathode is negative. And the battery is connected on its positive side to the anode, so therefore the anode is positive. Okay, let's take all this and apply it to some problems. So for 3 problems here, let's do the same 3 things. Let's first identify anode and cathode. Let's determine the flow of electrons, and let's find the signs on the anode and cathode. Let's take first this system where we have an expression. We have solid silver, nickel ions resulting in silver ions and nickel solid, and we're told it's an electrolytic cell. Well, first let's look at our table of reduction potentials and identify the relevant species. There we have the silver reduction potential, and here we have the nickel reduction potential. So we simply look at the values, and we see that the silver has the higher value, the nickel has the lower value. Therefore, we can assign the silver as the anode and the nickel as the cathode. In terms of the flow of electrons then, remember that electrons always flow from anode to cathode, because cathode is where the reduction happens. That's the red cat. And furthermore, for an electrolytic cell, the anode is positive and the cathode is negative. So that's one way to apply these ideas to this kind of an electrolytic cell. However, I'd like to show you another way to solve that problem, perhaps a quicker way, but it is important to understand what I just showed you. However, here's a quicker way to analyze the system. Notice what happens to the silver. It starts out as solid silver, and it ends up as an ion. So if you think about what that means in terms of silver and electrons, it means that the silver is losing electrons as it goes from solid silver with a reduction value of 0 to the +1. So it must be losing a negative. Minus a minus is a plus. As soon as you notice that silver is the thing that's losing electrons, and remember what Leo says, that loss of electrons is oxidation, and oxidation happens at the anode, you immediately can see that silver is the anode, and therefore the nickel is the cathode, and everything else follows from there. So a little bit faster way to solve that problem, but both ways are important. Let's look at another example. Here's a different kind of notation, and it's a little confusing at first, but we've got a lead system and a zinc system. So again, we can look at our table of reduction potentials, and there is the reduction potential for lead, and there is the reduction potential for zinc. and we can see that the lead has the higher reduction potential. They're both negative, but the lead reduction potential is closer to 0. Therefore, it is the larger number, the higher number. So therefore, the lead is the anode, and the zinc is the cathode, which means we can assign the flow of electrons, because electrons always flow from anode to cathode. And for an electrolytic system, the anode is positive and the cathode is negative. With this problem too, I'd like to show you another way to solve it. And that is to pay attention to these funny lines that are represented in this cell here. So just to remind you, this double line means separation by a salt bridge. So therefore, what's on the left of those double lines is one half cell. And what's on the right of that salt bridge is the other half of the electrolytic cell. And then notice there are these single lines. That is a phase boundary. It means between the solid and the solution phase on each case. So there's a solid lead electrode on the one side and a solid zinc electrode on the other side. But most importantly, there's a convention in writing these electrochemical cells that looks like this. The anode is always written first, and the cathode is always written second. So knowing that, recognizing that convention, you could really quickly say which of these is the anode, which is the cathode, and then knowing it's an electrolytic cell, you could determine everything else, where the electrons flow and what is positive and what is negative. Let's do one last example. Here is a system all contained in one cell, in one beaker, and we have platinum and gold as the two solid metals in solution. So looking at our table here, you can see that we do not have a value for platinum. However, what's next to the platinum is a hydrogen ion. So what we really have happening here is hydrogen ions gaining electrons, being reduced and turned into hydrogen gas. So there would be hydrogen gas, H2, bubbling up from around that platinum electrode. In this case, platinum is an inert electrode, and it's the hydrogen that's participating in the redox reaction. So there's the value for hydrogen, and there's the value for gold, and we see that gold's reduction potential is quite a bit higher than hydrogen's. Therefore, we can go ahead and assign the gold as the anode, and the platinum electrode, where the hydrogen gets reduced, we can assign that as the cathode. Electrons always flow from anode to cathode, therefore that's the electron flow. And for electrolytic cells, the anode is positive and the cathode is negative. Now, once again, I want to show you another way to solve this problem. And that is to just pay attention to the fact that this power source, this battery in this system, has its negative terminal on the side with the shorter line and its positive terminal on the side with the longer line. Therefore, we know the way that electrons flow. As soon as we know that, we can assign everything else from there. The anode, the cathode, the positive, and the negative. So, I hope this has been helpful to help you think about electrolytic cells and identifying their parts. We'll continue talking about electrolytic cells in the next video. Hope to see you there.